A set is a collection of objects we call elements. That could mean physical objects, thoughts, ideas, and concepts including mathematical objects, which will of course be the main focus for us. Possibly more importantly, a set is a way of packaging up objects which share similar properties in a meaningful way. Consider the set of triangles. We can unambiguously state whether something is or isn't in this set. This is in, so is this, but this shape isn't. It's not a triangle. This lack of ambiguity in what is or what isn't in a set is foundational to set theory. We can also make claims about the set and assess, again without ambiguity, whether they're true or false. It's true that an element of the set of triangles has three sides, but it's not true that the sum of the internal angles is 360 degrees. A set containing the numbers 1, 2 and 3 would be written like this, with curly brackets and the elements separated by commas. We can name the set. In this case, if we say A is equal to the set 1, 2 and 3, we can just refer to the set as A, which is much easier than saying the set containing 1, 2 and 3 again and again. To express symbolically that an element belongs to a set, we use this symbol. For example, if A is the set containing 1, 2 and 3, then 1 is in A and 2 is in A, but 4 is not in A. And we use the symbol for in, but with a line through it to denote not in. In most cases, we don't write out all the elements in a set, but we'll write a shorthand description using something called set builder notation. For example, the set of prime numbers could be written as capital P is the set of little p such that little p is prime. Here the little p is a variable which must satisfy some criterion we call the predicate, since its belonging to the set is predicated on this criterion. In this case, the predicate is being a prime number. Also notice we have a shorthand for the phrase such that, which is this vertical line. It's good practice when dealing with sets of numbers to declare explicitly which sets you're starting with. This is done before the such that symbol. For example, p in the natural numbers such that p is less than 5 is a completely different set to r in the real numbers such that r is less than 5. Two sets are equal if they both contain the same elements. If for all little a in capital A, little a is also in B, and for all little b in capital B, little b is also in capital A, then the sets A and B are equal. This definition means that the order of the elements doesn't matter. We only need to show that they share the same elements. So if A contains 1, 2 and 3 and B contains 2, 3 and 1, we say 1 is in A and it's also in B, 2 is in A and it's also in B, and 3 is in A and it's also in B. We then do the same for all the elements in B, and so we've shown that A is equal to B. It also doesn't matter if the elements are repeated. Like before, as long as every element in one set can be shown to also be in the other, we still have equality. Generally, we just write the elements in a way that's easiest to read, which usually means without repetitions and often in some sensible order. But just to be clear, it makes no difference to the set, just to us as readers. The size, or cardinality of a set, is the number of elements it contains. So if A contains 1, 2 and 3, then the cardinality of A is 3, and we denote the cardinality of a set with two vertical lines. If a set has an infinite number of elements, like the set of prime numbers for example, then it's perfectly fine to write the infinity symbol as the cardinality of the set.